Okay, so let's start. Today is the last lecture, and we have already learned what is called the Wald version of first law. Wald version of first law for black hole mechanics. And in the last class, we wrote down this law, kappa by 2 pi. I'm putting h bar to 1, delta S equal to delta M plus omega delta J. Okay, this J is not the current, but the angular momentum. Okay. Okay. And then if you remember, here this is defined on the horizon. Particularly the entropy S, okay? I told you that this is given by this expression. If the Lagrangian, let's say my theory has a Lagrangian scalar, which is G alpha beta R alpha mu beta nu. I'm not considering, for simplicity, things which Lagrangian scalar builds out of the derivative of the curvature, covariant derivative of the curvature. I'm stopping at only at the curvature. But in principle, you can do that. What will happen is that there will be some extra term in the entropy expression. Otherwise, everything will remain same. And then this, I told you, is given by this expression, gamma delta, Q alpha, sorry, my mistake, epsilon alpha beta, epsilon gamma delta, square root of sigma, d minus 2x. And this integration, I told you that it has to be done on the bifurcation surface of the Killing horizon. But I also told you that if you could also do, if it is a bifurcated Killing horizon, then after evaluating at the bifurcation surface, if you go to any other arbitrary cross section, you can show that the difference vanishes on the horizon, and therefore ultimately you can actually evaluate it in any arbitrary cross section of the horizon. Okay. Sometimes we can denote this quantity by Q alpha beta. Okay. If you remember that this is related to the dual of the other charge, which is n minus 2 form. So suppose this guy is actually 2 form. And sometimes we will write this integration as minus 2 pi integral Q alpha beta epsilon alpha beta. Sorry, something is wrong. Q alpha, sorry. This should be given gamma delta. Okay. Epsilon gamma delta and gamma delta square root sigma d minus 2x. Convention wise, 16 pi g is included in this. Okay. So please remember that. Okay. Otherwise, you will get your factors wrong. Okay. So let's see what happens to GR. Okay. I mean, maybe let's do it a little bit general. Let's think of your Lagrangian to be a function of R only. Okay. Well, assume that it's only a function of Ricci scalar. These are so-called f of R theories, like 1 plus R square plus whatever you can think of. Okay. So let's write it a little bit carefully. I write this as R plus some f of R. I'm keeping the R term separated so that I can identify the GR part. And if you want, you can put arbitrary coefficient alpha here. You don't have to. If you want, you can put it. Okay. So therefore, if alpha goes to 0, you will have GR result. Okay. So you can track GR. Okay. Let's see what will happen for this guy. Okay. How do I calculate this derivative? Okay. So therefore, I need to calculate this object. How do I do that? I start with, so again, I should tell you that this has 16 pi g built in. 1 by 16 pi g is there. Okay. So let's see. I have LL del R alpha beta gamma delta. This is what I have to calculate. The partial means you treat metric Where am I? Yeah. So partial means this is a function for metric and curvature. You treat the metric and curvature to be independent of each other. This partial means when you take the derivative, do not take the derivative of the metric. Okay. That's the meaning of this. So let's go ahead and calculate it. So this will be 1 by 16 pi g del del r alpha beta gamma delta, and then I will have some L as a function of r. Okay. So therefore it is clear that this will be L prime of r. Okay. And then you will have 16 pi g. Okay. And then I will have del r alpha beta gamma delta. Okay. Note that one has to be a little careful in taking this derivative. This particular tensor, when it goes up, it becomes some tensor P alpha beta gamma delta. It has all the symmetries of curvature tensor. Okay, so you have to be careful that the result you get out of it should have all the symmetries of the curvature tensor. Let's go ahead and do it. So I'll write it as L prime r 16 pi g del r alpha beta gamma delta, and the r I will write r alpha gamma r beta delta r alpha beta gamma delta. Okay. Agreed? In principle, I should have taken a different index here and all the deltas, but it's okay as long as you understand. Okay. So therefore, it is clear that this object then becomes L prime r 16 pi g alpha gamma g beta delta. Okay, should I stop here? Is it okay to write this thing? Is it okay? Is it okay? Is it perfect? Or should I do anything more after taking the derivative? Yeah, but then remember I told you this object should have the correct symmetries. Okay, so better, but this does not. For example, this object is antisymmetric in alpha beta and gamma delta. It is not. Okay, so therefore I should explicitly antisymmetrize it. Half g alpha gamma g beta delta minus g beta gamma g alpha delta. You should see this is antisymmetric both in alpha gamma as well as beta delta. Okay, sorry, alpha beta and gamma delta. This is antisymmetric in alpha beta as well as is antisymmetric in beta gamma delta. Is that clear, everybody? Okay, so therefore this object has all the symmetries of the curvature tensor. Okay, at least indices symmetry. Okay, good. So therefore, what I get is that L prime is 1 plus alpha f prime r, then 32 pi g alpha gamma g beta delta minus g beta gamma g alpha delta. Okay, let's carry on. Now what should I get? Let's put it here. Okay, in this square, in this expression here. So I'll get entropy as equal to minus 2 pi integral on the cross section. And then what do I have? I have 1 plus alpha f prime r divided by 32 pi g, and then I have this object g alpha gamma g beta delta minus g alpha beta gamma g alpha delta, and then I have beta g gamma, and then okay, agreed, everybody? So this is antisymmetric in alpha beta, this is antisymmetric alpha beta. So I'll get minus pi cancel out 1 by 16 g integral 1 plus alpha f prime r. Okay, and then I'll get a factor of 2 g alpha gamma g beta delta epsilon alpha beta and epsilon gamma delta square root of sigma t minus x. Agreed? Everybody? Okay. So therefore, this become minus 1 by 8g integral 1 plus alpha f prime r. Okay. Then this is g alpha beta epsilon alpha beta square root of minus g epsilon sigma. Okay. Agreed? Last time we did it. What was the result? Epsilon alpha beta minus 2. So therefore, we get a result that this is nothing but 1 by 4g integral 1 plus, so that minus sign become plus now, alpha f prime r square root of sigma d minus x, as expected. Okay. So if you put alpha equal to 0, you go back and get general relativity, 1/4 of the area. Okay, clear? So you know how to do it, okay, these calculations. But if there is a correction to general relativity, you can clearly see there is extra term. Entropy is no longer proportional to area. Okay. Everybody, you should try. In fact, in the tutorial, we'll try. In the meantime, before the tutorial, if you don't take lunch, you can try this. That suppose I have L equal to 1 by 16 pi g r plus alpha r alpha beta r alpha beta. Okay. Okay. What should be the entropy according to this formula? Okay. This is still a function of r and r alpha beta gamma delta, because Ricci tensor, I can think of a contracted curvature tensor. Then you should be able to follow the same result. Again, the crucial thing is that after you done this derivative, you have to ensure that this resulting object has the correct symmetries. Okay. Only then you will be able to get the correct factors. Otherwise, you cannot. Okay. Okay. Good. So please check this. Try this. Good. This is a clear algebra. We can always do it. Let's come back to a little bit of physics again. Yeah. Yeah, that's the assumption. That's the assumption. What is the other prescription? I mean, I also don't know. Well, I mean, what you can do if you know an exact solution, or if you know a particular theory, you would be able to find the entropy of that black hole. So historically, if you look at it, even before Wald's paper, Ted and Myers, I think, wrote a paper about the entropy of Lovelock theories. Even before this Northern Church business came into existence, they have shown that entropy gets a correction. But that is for a particular theory. Okay. In that particular theory, what they did is that they followed an procedure same as that of the what Hawking and original paper, Hawking, Bardeen, all those guys. Okay, but for the Lovelock theory. Okay. So you can start with the Komar mass at infinity, integrate on a 3 surface, and obtain everything for this particular theory. You can do that. But even, I think even before that, there's a paper by, there is a interesting work by Matt Visser, okay, who probably the first person who understood that entropy will be different from area if you go to other things. Okay. So in a particular theory, you may be able to do it. But in a general theory, the prescription, this is the all we know. Numeric solution means? Okay, but that has nothing to do with this formalism, right? I mean, look, the fundamental assumption is that there is a black hole solution. And f of r gravity, at least we know one, that is the Schwarzschild solution. Okay. But f of r will have more solutions, definitely, because it's a higher derivative theory. Like if you have Lovelock theories, we don't know any rotating solutions. Well-behaved rotating solutions are not known. So it is true, we don't know the exact solution. And I mean, you can think of some theory which does not have any solution, okay, at least. Okay. But one would expect that solution exists perturbatively. If you go small departure from general relativity, at least when these alphas are small, one would expect there will be a solution similar to general relativity, unless there is something very crazy going on. Okay. So even if we don't know the exact solution, this theory allows us to calculate. For Lovelock, you can test it because you know the explicit spherically symmetric solution. So you can actually go back and test in that particular solution where things are correct. Okay, good. So let us now go back to the expression of entropy. Okay, so it is clear I will be able to write the entropy, the black hole entropy, as S for any theory 1/4 integral on this some cross sections of the horizon. Okay, 1 plus some rho square root of sigma minus 2x. Okay, 1 is for GR and rho is for your theory. Okay, so rho we don't know. Wald has told us that rho is something like what the Wald has shown us, that this particular part, if you look at it, okay, is something proportional to rho. Okay. So, but whatever the expression of rho is rho. Okay. We will be able to calculate by taking the derivative of the Lagrangian. For example, here rho is this alpha f prime r. Okay. Clear? But and of course it is clear if rho equal to 0, what we get is GR. I should be always able to do that. What will rho consist of? Rho will consist of horizon objects. Okay. It has to be constructed out of the local metric curvatures, okay, derivatives of curvature, whatnot, some contraction of the curvature in different direction across the horizon and along the horizon, but evaluated on the horizon. Let me again emphasize, there is no reason for rho to only depends on intrinsic geometry, unless you have a very special theory. It could also depend on extrinsic geometry. For example, the extrinsic curvatures, okay, of the horizon cross section embedded in the horizon. There are examples when rho depends on that. It turns out, at least for Lovelock class of theories like Einstein-Gauss-Bonnet gravity, this rho is actually intrinsic to the horizon. Today, we will prove in the tutorial. Okay? But we can always able to write rho according to this. Okay, and let's assume the theory which we are working with, is the equation of motion is of this form. Okay, is G alpha beta plus some alpha H alpha beta is equal to 8 pi G alpha beta. I don't know what these H alpha betas are. In principle, they could depend on higher order in curvatures. Okay, so if you look at RABCD, and whatnot, they will depend similarly on H will depend on similarly RR kind of contraction, and alpha will have suitable dimension to take care of the things. Okay, if it is R square, alpha will have some length square dimension. It will take care of the dimension in both sides. Okay, so this is my entropy of my theory. Okay, and this is the equation of motion. Okay, now with this, what we now want to do, so what we call a physical process first law. So what is the idea? Okay, physical process. Physical process. Again, as always, the first mention of physical process first law you will find in Wald's book, Quantum Field Theory in Curved Spacetime, that red book. He has few lines, cryptic lines, and there he first time mentioned that how to do physical process law, but then it is generalized by Ted and Parantiri, you can look at their paper called, I think, called On Horizon Entropy or Horizon Entropy. That's the name of the, I think I will add it in the set of references. There they discusses that how to do physical process first, so not only for black hole horizon, for a large class of what is called the causal horizons, okay? But we are interested here only for black holes. So if you look at physical process first, the first and important thing to understand, let's look at this Wald formula. This delta is first of all variation in the space of solutions, okay? Not only that, this side is evaluated on the horizon, this side is evaluated on entropy. This is not something we do, okay, in our regular life, okay, when you look at change of things, okay? So therefore, one would expect that I should be able to calculate a more local version of the first law, where I will look at flux of energy going into the black hole, okay, and as a result, how the entropy changes. And I should be able to write down equality between change in entropy with the flux of the energy going into it. Now, easier this can be, the saying is easier, doing is difficult, because you have to be careful. What do you mean by flux of energy? If the black hole is perturbed, okay, everything is changing with time, there is no notion of a killing vector anymore. Then how do you even define the energy flux? Is ambiguous, okay? So we will do it what is called perturbatively. So therefore, the assumption will be, we have a killing horizon, there is a killing vector. On the top of the killing horizon, there is perturbation. This perturbation could be matter falling into the black hole, or it could be gravitational wave entering into a black hole, or whatever. At the result of this perturbation, area or slash entropy is increasing. Okay, area for GR, entropy for more general cases. And we will be able to measure the energy falling into the black hole with respect to the background killing vector. So there will be a background killing vector. With respect to the background, I will measure how much energy has crossed the horizon. Okay, that will be my measuring standard. Okay, so let's see how we actually perform this calculation. And this calculation will involve extensive use of the Raychaudhuri equation. Before we go to, we understand some part of the geometry of the killing horizon. So I think yesterday or day before yesterday, Shubhayu has derived the surface gravity for you. So remember that the definition of surface gravity was obtained from this equation, kappa xi beta. This is only valid on the horizon, okay? And this tells you that using this equation, at least for the Bifurcated killing horizon, we've proved that surface gravity is a constant. It does not change along all the directions of the horizon surface, okay? Both in the killing direction as well as the tangential direction, transverse directions. Good. So this guy is the killing vector, which is null on the horizon. What it means is that I should be able to, so let me parameterize this guy by a parameter called V on the horizon, okay? V is a parameter which parameterizes this guy on the horizon, okay? And it is clear from this equation, this too tells you this is a non-affine parameterization. Why? Non-affine parameterization because this is a geodesic equation. It's a non-affine geodesic equation. This side has kappa xi. Okay. Yeah. This is, you must have learned for null geodesics, that for null geodesic, I should be able to write down both affine and non-affine parameterization. You can do it for any geodesic. Okay. Non-affine parameterization. Sometimes calculation is, okay, you can always do it any parameterization. Sometimes calculation is easier if I define affine parameterization. Affine parameterization. So what do you mean by affine parameterization? From xi, I create another vector field. See, xi is a generator of null hypersurface. Okay, so it is hypersurface orthogonal to begin with. Okay, because this is the null generator. But with that, I can also define another guy, K alpha. This is also null vector, but this is given by del del lambda of A, where I say affine, lambda is affine. Okay. So if you do that, now the question is, what is the relationship between lambda and V? And since this is affine, I have a relationship K alpha del alpha K beta must be equal to 0. Okay. So this is non-affine, this is affine. So there must be a relationship between this affine parameterization and non-affine parameterization. It's a very simple thing. You can do it one line by looking at these two equations, how lambda is related to V. I will give you the direct result. Show that this is a first order differential equation solution. You will have lambda equal to kappa inverse e to the power kappa into V. Okay. It's clear. You will be able to show that. Okay. That these two parameterizations are related by this equation. Most importantly, understand that if V goes to negative infinity, so sometimes V is called killing time and lambda I will call affine time. If V goes to negative infinity, lambda goes to 0. Right. Okay. So therefore, you can show that xi alpha, which is del del V of alpha, is nothing but lambda kappa K alpha. This is nothing. You take del del V, you write it as del lambda del V into del del lambda, you'll get the result. Okay. So I will write it. So this is important. Note. Xi lambda equal to 0 when lambda is equal to 0. Okay. So therefore, lambda is a parameter which moves along the horizon. Every lambda equal to constant surface is a cross section of the horizon. And the dimensionality of that cross section is codimension 2, n minus 2 dimensional. Therefore, lambda equal to 0 is the what? Where xi is 0 and which is not one dimensional. What is the name of that surface? Bifurcation surface. Good. So lambda equal to 0 is my bifurcation. You will see, just like there, bifurcation surface played the important role, crucial role in derivation of Wald entropy. Physical process first law also, bifurcation surface will play a crucial role. Okay. So note that this. Okay. Now, just like we did it with the xi, so now K alpha is the affine null generator. By definition, that is generator, which is by definition a hypersurface orthogonal of the horizon. So therefore, K alpha is 0. Okay. So just like we did it with xi, we will construct a basis using K alpha as one of the basis direction. We will define another null vector, L alpha, such that L alpha equal to 0, but K alpha, L alpha will be normalized to -1. This is again akin to V direction and U direction of the Schwarzschild geometry. Okay. And then we will complete the basis with this K alpha, L alpha, and a transverse metric which we call sigma alpha beta. And last time we wrote down, but sigma alpha beta is equal to G alpha beta plus K alpha L beta plus K beta. This is again important. So what I did is that this is the d minus 2 surface. I defined some vector K and some another null vector L alpha, which is outside the horizon. And on this, I have sigma alpha beta. Okay, very crudely speaking. Okay. So I've achieved what is called a d minus 2 plus 1 decomposition. D minus 2 plus 2 decomposition. Okay. Clear? This is the structure of my geometry. Okay. Good. And lambda equal to 0 is my bifurcation surface. So each time lambda equal to constants, okay, these are cross section of the horizon. Okay, this is the geometry to begin with. Okay. Okay. Now what we will do? We will put up object. Okay. One central equation which will be very, very important. Let me go back there. Will be important, as I told you yesterday, which is Ray-Choudhury equation. Null Ray-Choudhury equation. And null Ray-Choudhury equation basically says how the expansion, rate of change of expansion or the second derivative of the area changes across the null direction. Okay. And this is familiar equation. All of you should know this. This being the centenary year of Ray-Choudhury. I mean, all the relativists should know the derivation of this equation, at least this year. Next year you can forget. Okay. Is equal to minus theta square by d minus 2, then minus sigma alpha beta. There is a plus omega alpha beta term, but I'm throwing away that term, the rotation scalar term, because k alpha are null generator. By definition, they are hypersurface orthogonal, and therefore by Frobenius theorem, omega alpha beta vanishes. So there is no omega alpha beta, but I have a Ricci curvature term, a Ricci scalar term, Ricci tensor term. This is going to be a central equation. Which is going to play an important role in this derivation. Okay. Good. Look, this equation does not depend on the theory of gravity. This is just a general fact, geometric fact. Okay. How the null horizon expansion is changing. Theory of gravity comes when you replace R alpha beta with respect to T alpha beta. So if it is Einstein theory, R alpha beta, K alpha, K beta is T alpha beta, K alpha, K beta. If it is not Einstein theory, there will be extra curvature dependent now. Okay? Good. Let's go ahead. So, we now want to calculate this delta S. I require a little bit more space. Let's go ahead and calculate. So, S is 1/4 integral 1 plus rho square root of sigma d minus 2x. You have to be a little careful. Rho depends on geometry, so rho will change if you change lambda in time dependent setting. Sigma will also change because there is expansion. Okay. Okay. So let me write down what do I mean by delta S. So I put a suffix lambda. What it means is that I'm changing variation, and the variation is how the things are evolving from one cross section to other cross section, and why things are changing in one cross section to other cross section. Because this cross section are nothing but the cross sections in time. Things are falling into the black hole. There is a time dependent geometry. As a result, both the area, rho, everything is changing. Every slice, the geometry is changing. Of course, if it is a pure killing vector, delta S will be 0. Now the assumption is that there is something which is falling into the black hole. Okay. So this delta is different from the delta for Wald. Of course, there is a relationship in for Wald derivation, at least both are Wald derivation. Okay. Okay. In our previous 4 classes, we are considering variation in the space of solutions. But here, it is actually changed because I'm going from one lambda to other lambda, and in between things are falling into it. Okay. So therefore, sometimes you use the word physical. Well, I don't know what is unphysical, but anyway. So what is this object? Is then 1/4 remains as it is. There is a G here, which I'm not writing. Huh? Maybe I can keep it G. G is good. Okay. So therefore, this will be what it would be. Let's say this will be dd lambda of 1 plus rho square root of sigma. Okay. Sorry. Square root of sigma. Then what should I get? Tell me. D lambda root sigma d of d minus 2x. Okay. Clear? Okay. That's the change. Yeah. Now the integration, earlier integration was a cross section. Now the integration is a portion of the horizon. Okay. So first integration was a 2-dimensional surface or d minus 2-dimensional surface. I integrate between delta lambda equal to 1 to lambda equal to 2. I get an integration on the portion of the horizon. Okay. Clear? That means this integration, this contains integration over the 2-dimensional surface plus another integration between lambda 1 to lambda 2. That is why dd lambda is there inside. Yeah. Yes. Oh, good. Thanks. Yeah. Okay. Okay. I meant it inside. Okay. Let's go ahead and take the derivative. Okay. So what should I get? 1/4g integral. This integral is a 3-dimensional integral. Don't forget it. Okay. That means 1 will not work out. Then I'll have rho. Let me write it theta, and then you will explain that if it is correct, d rho d lambda, and then I will have 1 plus rho. Then I will have theta. Okay. Sigma x. Is it okay? Where the expansion is given by dd lambda into everybody. Okay. That square root of root sigma comes out. Okay. Clear? Okay. Okay. So let's write it down again. This is nothing but delta lambda s is nothing but 1/4g. Let's see what do I get. Integral. Keep the 1 as it is. 1 is, sorry, theta as it is. And then we will get plus and rho theta, rather 2 rho theta, right? Is it what we will get? 2 rho theta? Right? 2 rho theta. Okay. Is it fine? Yeah. 2 rho theta plus, then I will get d rho d lambda. Okay. Agreed? Everybody? And then I have sigma and d lambda d of d minus 2x. Agreed? Just let me check if everything is there. This is theta, 2 rho theta, and d rho lambda. Agreed? Any problem? Yeah. You're asking something. Is that okay? Everybody is in agreement? Huh? Yeah. Because there is a rho theta here. See, this dd lambda acts on root sigma. Okay. So according to this formula, dd lambda of root sigma is nothing but theta into root sigma. I took root sigma out here. So only theta will contribute. This is that rho theta. Okay. 1 plus rho. Yes. No, because this guy will come out. I take dd lambda of this. There's a theta. Okay. And oh, there is no rho theta here. That's what you are saying, right? Sorry. My mistake. Yeah. Yeah. Is this fine now? Okay. This is fine, right? Yeah. That's why there should not be a factor. Good. That was a test. Okay. Good. So you can clearly see if I put rho equal to 0, which is for the case GR. Okay. In that case, I will get S equal to GR 1 by 4G integral theta of sigma d lambda d minus 2x. Agree? Okay? Which is exactly what we expect, because for GR, entropy is the area. So entropy change is nothing but integration of the expansion along the null generator, and then integration on the, because this theta is defined locally, so integrate on two-dimensional surface and integrate on theta. This is the total rate of change of the area, and that is what the entropy is. Okay, for GR it is satisfactory. So therefore in GR, this object is very, very geometrical. This is nothing but the change of the area per unit area for a pencil of generator. Okay. Whereas this object, for a general theory, call it capital theta if you want. Okay. This object has nothing to do with expansion. Okay. Because now there are geometric quantities rho. Okay. So, but you can still call it something like change in entropy. Change in entropy per unit entropy. Or per unit area rather. Okay. So it is, if it is GR, entropy is area, at least proportional to the area, you go back to your geometric expansion. Otherwise, this is some object, it has a name, capital. It has nothing to do with geometry. But it has a thermodynamic meaning, if we believe that entropy and everything are serious objects. Okay, good. With this, let's go ahead further. What should we do now? What we'll do a trick. We'll do integration by parts of this formula. Okay. We'll take lambda as one of the variable, and this guy is one of the variable. We'll do integration by parts. So delta will be given by 1 by, so remember this one has to be very careful. Huh? This is integration on the 3 dimension. Okay, so portion of the horizon. So 4G. If I do integration by part, then again it's integration on the cross section. Let me write it and you will see theta plus rho theta plus 0 t lambda. And this integrated on lambda 1 to lambda 2 d minus 2x. Okay, and there is a lambda. Okay. This is the first term minus 1 by 4g integral. Again on h, this guy, there is a lambda. Okay, then I will have d lambda of this entire object, theta plus rho theta plus 0 d lambda square root of sigma, this entire object d lambda d minus 2. Is that clear what I did? See, the first thing is d lambda. If I integrate from lambda 1 to lambda 2, I get this entire thing evaluated at lambda. D lambda integral give me lambda. So I evaluate everything at lambda 2 to lambda 1 only on the bifurcation, only on the cross section of the horizon. Square root, where is square root? Ah, ठीक है. Forgive me. Okay. Okay. Rest of the terms are okay. And then again, d lambda integral will give you lambda. Then derivative acts on the second guy, and you get this object. Lambda is the first, and that object in the bracket is the second. Is that clear? Okay. I'll come back to this part again. Let us understand this object. Okay. So this entire object is evaluated between two cross sections, lambda 1 to lambda 2. Okay. Now, of course, ideally this is not 0. Okay. It will contribute some boundary term. Okay. Now we'll play an important role. We will calculate calculate entropy change from bifurcation surface. That means my lambda 1 is set to lambda equal to 0. Okay. We want to calculate entropy change between any two surface. So I will calculate entropy change between starting from the bifurcation surface. Okay, of the unperturbed horizon. Okay. And at bifurcation surface, according to our construction, what is the value of lambda? 0. So what will happen for the boundary term evaluated at bifurcation surface? It will give me 0. Okay. So, and the final cross section. What will be the final cross section? Will be considered in the asymptotic future. Where the horizon, where the perturbation, when the perturbed horizon, settle down to a stationary state. So before I explain, note that one has to be a little careful. I am saying lambda equal to 0, this term vanishes. Okay. What it means is that this guy is inside cannot have a fall off if you move along lambda equal to 0 faster than 1 by lambda. Then the product will not be 0. Okay. You have to be a little careful that this gives you certain regularity condition on the horizon, on the bifurcation surface. That expansion and the derivative of the d rho d lambda, they should not diverge. Okay. Higher than 1 by lambda. Okay. Otherwise, this product will not be ensured go to 0. Okay. So some kind of regularity is already assumed at the bifurcation surface. Okay. But what about the final cross section? So I will say, I will integrate the final cross section where all this perturbation and whatever I have done has died down. Okay. And the black hole has settled down to an asymptotic stationary state. This is a big assumption. There is absolutely no guarantee that for an arbitrary theory, all black holes are stable. If I do perturbation, after a certain time, all the perturbations will die down, quasi-normal modes and everything will have the right sign, and I will have another stationary black hole of little bit of different or higher mass. Okay. There is no reason for this to happen. Okay. But if it does not happen, there is no point in doing the physical process first. So that means the perturbations is not a perturbation, it will grow, and then it's completely non-equilibrium. Things will destroy, horizon will destroy, we'll have naked singularity or whatever. Okay. So then that's not what we do. Okay. So the assumption will be I'll perturb the black hole, perturb, area changes, but after some time, the black hole settle down to a new equilibrium state. Okay. So that I can neglect all possible forms of killing vector, Lie derivative and expansion of the covariant object to 0. That means if it is again at the final cross section, everything is stationary, then theta is 0, and d rho d lambda is still 0. Okay. So final cross sections is considered to be stationary. Initial cross section is considered to be at the bifurcation surface. I am trying to evaluate what is the area change between these two surfaces, these two cross sections, these two times. Okay. Okay. So this is sometimes called an integrated version of the physical process first law, that I'm trying to understand what is the total entropy change if I integrate from the bifurcation surface to the end of the perturbations. Okay. So in that case, both the boundary terms I can net to 0. Okay. So boundary terms boundary terms do not contribute. Because rho is scalar, this is something like a Lie derivative. Rho is constructed out of curvatures and whatever. Okay. Whatever modified gravity is some curvature. So Lie derivative will be 0 in the stationary future. It is constructed at a cross section. So let me draw this. Maybe I'll draw it here. If there was no perturbation, let's assume the picture would be like this. Okay. This is lambda equal to 0. This is generators of the old black holes. Okay. And this is some lambda. Okay. Nothing. So you can think of this length is like an area. Nothing changes. Okay. Now, fortunately or unfortunately, there is some matter flux into the black hole. As a result, the black hole area changes. Okay. And it settled down to a different state. Here. Okay. Let me think of after this time, area change, everything goes out, and then again it is stationary future. Okay. And you can take a cross section here, call it lambda f, and you're considering what is the entropy change between integrated in this thing. If it is area, you're asking what is the difference between this area and this area. Okay. Clear? It is not any two cross section. Okay. If you want to know how to do physical process cross section for any two cross section, you have to do a little bit more work. Okay. I can send you the reference. Okay. Let's go ahead. Oh, good. You maybe noticed that I have here drawn the event horizon expansion even before this matter hit the horizon. Okay. Okay. Think of it why. Oh, I probably require this formula, but anyway, you already have it. Okay, good. So therefore, I will completely ignore the boundary term. So what I am calculating now, therefore, integral lambda equal to 0 to lambda f delta lambda s. Okay. And I call this guy to be some delta s. Okay. So this is integrated change from bifurcation surface to stationary future. And therefore, delta s is given by minus 1/4g integral h lambda. Again, remember the limits here. These are two integrals. One integral is on the d minus 2 surface, and there is a lambda integral which goes from lambda equal to 0 to lambda f. Lambda f is stationary. Okay, the cross section. Yeah. I can't hear you. This is smooth. There is no. Why would there be a corner terms on the horizon, black hole horizon? This is like saying at some point theta goes to 0, and after that everything. So let me not go into what happens for. There is a theorem by Penrose that there is no caustic in the future. Okay. Provided cosmic censorship holds true. All this comes from there. Okay. So basically, this is an assumption. Again, it's a physically motivated assumption, but for all theories, this need not be true. Okay. Then you don't have physical process. Okay, let's go ahead. So therefore, I have this object, lambda dd lambda. Can you tell me what is inside theta plus d rho d lambda plus rho theta? Okay. And then I have square root of sigma d lambda d minus 2x. Okay. So let's take the derivative inside. I will have minus 1/4g integral h lambda d theta d lambda plus d2 rho d lambda 2 plus rho d theta d lambda plus theta d lambda d rho d lambda. Then this guy acting on this plus theta plus d rho d lambda plus rho theta. And this will give me again theta, entire thing, square root of sigma d lambda. Just check if I need any extra term by law of requirement. Is it clear? Okay? Okay? Okay, so let me again explicitly write all those terms. Now, what is this d theta d lambda? I can use Ramanujan equation. Okay, let's go ahead and write it. Maybe I'll go back there, okay? Because I need a long portion of the board. Should I, is it okay if I write it? Can you see it? No, okay. I'll write it here. Yeah, sorry, I'll require a bigger portion of the board. Okay, let's see. What do we have? Okay, so delta S. Minus 1 by 4g integral over the portion of the horizon between lambda 1 and lambda 2. Okay, now lambda 0 and lambda f. Lambda minus theta square by d minus 2 minus sigma alpha beta minus r alpha beta k alpha k beta. That's my d theta d lambda part. Then I have d2 rho d lambda 2. Then I have rho, again d theta d lambda part. Okay. That means minus theta square by d minus 2 minus sigma alpha beta minus r alpha beta k beta. Then I have another term theta d rho d lambda plus theta, sorry, d rho d lambda. Okay. And then I have the last term plus theta square plus, tell me again, theta d rho d lambda. So I'll put a 2 factor here, plus 2 theta square, and then I have rho theta square. Okay, and the entire thing, square root of sigma d lambda. Okay, a small expression. Okay. Okay. Agreed? More assumption. Okay. Linearized version. Linearized. What does linearized version means? So this thetas, any question or any question? These thetas and sigmas are the by perturbations. They are proportional to the order of the perturbation. So for example, if I have a capital mass black hole on which I put small mass black hole m, a small particle m, okay, then thetas and sigmas will be proportional to smaller. Theta square and sigma square will be proportional to m square. What I will assume is that both thetas and sigmas are much smaller. They are changes, these are changes, much smaller to the length scale provided by kappa. I can think of a dimensionless object which is kappa into theta. Kappa is the surface gravity of the background horizon, which is related to the mass of the background horizon. So I'll assume something like kappa into theta much less than 1. Okay, sorry. Oops. Okay. Which means compared to the thick mass of the black hole, the perturbations are small. Okay. Because I want to only calculate the Clausius version of the first law. of thermodynamics. So I'll only look at the linearized perturbation. So therefore, all the second order part I will neglect. Okay. So what are my second order part? Let's put this color. This is second order. This is second order. This is not. Okay. Because if it is perturbation, RAB is proportional to perturbation TAB, and therefore this could have first order first order part. Okay. This guy again can have first order part. Okay. This is second derivative with respect to lambda, but perturbation wise it is linear, first order, second order, all are there. Again, this guy could be second order. So no, this is first order. Okay, this I throw away. I'll throw away this part, theta d rho d lambda. Okay, both are first order. Their multiplication is therefore second order. Similarly, I throw away this object. These are the terms I will throw away. Okay, I will not consider them because they are higher order. Okay, in perturbations. Okay, if I do that, what do I have in linear order perturbation? Let me write it down, delta S. So therefore, first we have integrated version. Now you have a linearized integrated version of the physical process. Let's see what does it give. It gives me minus 1 by 4g integration lambda. What remains? Minus R alpha beta K alpha K beta. Let it be. Then I will have d2 rho d lambda 2. Let it be. Then I will have minus rho R alpha beta K alpha K beta. Let it be. And that's all. Sigma d lambda d minus. Okay? Same thing. Yes, exactly. But they, with respect to what? You have to put a length scale. The length scale or time scale is given by the background mass. Okay. Small. So this thing is small. First order. So basically, we are only looking at first order perturbation. Yes. Because rho, this is definitely first order. Okay. But rho has non-zero value on the background stationary also. This is the entropy part of correction to entropy. So therefore, this is first order. All quantity, it has a first order contribution. So we'll only look at that. Okay. Rho has a non-zero value on the background because rho is like F prime R for the FO for gravity. Okay. Is that clear? Still, I have not used the equation of motion. Okay. It is still a geometric object. Okay. I took some rho and then let's use the equation of motion. Equation of motion is G alpha beta plus H alpha beta. Did I use alpha? I just put H alpha beta, right? Equal to 8 pi G T alpha beta. Okay. So if I use K KB, this guy will become R alpha beta, K alpha K beta. Note that inside HAV also there are to be terms proportional to small g alpha beta. They will not contribute when I take K alpha K beta. Okay. But I will write always, I don't know H alpha beta. So I just call it H alpha beta, K alpha K beta. And this is 8 pi G T alpha beta, K alpha K beta. Okay. Okay. So we are going to use this equation of motion. Let me not waste the part of the board and do this calculation here. Okay, so what I'll do, instead of this guy, I'll replace this guy. Okay. Let's see what will happen. Where alpha? Here, did I put a alpha? Let's absorb it into each other. You can put alpha if you want, doesn't matter. Okay, so what do I get? Minus delta S equal to minus 1 by 4g integral lambda. This becomes minus T alpha, 8 pi G T alpha beta K alpha K beta. Then I will have plus H alpha beta K alpha K beta. Okay. There is a minus sign outside, remember. And this I can write K alpha K beta del alpha del beta rho. This is not exactly this. This is only true for affine parameterization. Please check it. Okay, because what is this object? This object is K alpha del alpha K beta del beta rho. Okay. Only for affine parameterization, I can take the K out. Okay, and therefore I will have this object. Then what is the other term? That's all, right? Oh no, there is another term. Minus rho R alpha beta K alpha K d lambda minus. Okay. So let's take things, everything. So all of these terms will be 0 if I consider GR. On GR, H is 0, rho is 0. Okay. So let's see. What do I get? So delta S is equal to 1 by 4G. So I'll get 2 pi. Okay. Okay. Then what should I get? 2 pi and then integral lambda T alpha beta K alpha K beta, right? K alpha K beta d lambda d minus 2x. Okay, this is the first term. Then I have few more terms plus and 1 by 4G integral. I write that term first, lambda rho R alpha beta K alpha K beta remains as it is. Then I will have minus H alpha beta K alpha K beta, then minus d2 rho d lambda. I write it in this way. D lambda. Agreed? Everybody is in agreement? Okay? Okay. Now let's do something. Let's look at the GR case. Okay. This is true for any arbitrary theory where the correction to H alpha beta, equation of motion is given by H alpha beta and correction to entropy is given by rho. Okay, clear? This is an arbitrary for any theory. This is true as long as the equation of motion correction is given by H alpha beta and entropy correction is given by just this one. I just kept it as it is. Because we don't need to. We already got this part. Because this is a part which will go to 0 if Einstein's equations are true. We just keep it in this way. You can do it, it doesn't matter. Okay. Okay. So let's now consider to the case general relativity. What GR? Entropy is area and equation of motion is R alpha beta or capital G alpha beta, right? So therefore, GR limit is where this entire term is set to 0. Both rho is 0 and H alpha beta is 0. Okay? Yeah. Here everybody is a fan of root sigma. Okay. You know what I should have done? I should have called it dA and what we did. Anyway, yeah, of course. Okay. Okay. So this part goes to 0 for GR. Okay. So therefore, GR, I have a very smooth equation. Delta S equal to 2 pi integral lambda T alpha beta K alpha K beta root sigma d lambda. Okay? Okay? Now I will do something interesting. Look at this part. There is a lambda, there is a K. On the background killing horizon, remember, I have defined somewhere this object. This is only true if I have pure killing horizon. Okay. It is not true on, because K alpha, I can think of K alpha to be the generator on either perturb or unperturbed. They need not be same, although they can be pulled back into same, but let me not go into there. Okay. So, but this T alpha beta is already first order. It already contains the perturbation. So everything I can evaluate on the background killing horizon. Okay. So, because I'm only looking at linearized term. So therefore, I can write this object as 2 pi only up to linear order T alpha beta xi alpha K beta root sigma d lambda d minus 2x. I can, but there will be a kappa, right? 1 by kappa. Okay, because there is a kappa which goes down. Okay, again, I can take kappa outside because I have already proven this integration is on the horizon. Everywhere kappa is a constant. Okay, because I'm using bifurcate killing horizon. Clear? Now let's interpret this guy. What is this object? This is nothing but the area element on the horizon. Nulls. Okay? And therefore, I have equation kappa by 2 pi delta S with all this massaging integral T alpha beta xi alpha. This is my, okay, please understand this integration is between horizon, but between lambda equal to 0 to lambda equal to lambda f. Lambda f is the final cross section where everything is again stationary. This is what we call integrated Herschen of the integrated physical process. Okay. What it means is that if I again interpret kappa of the background perturb horizon, unperturbed horizon, as the Hawking temperature, okay, then this is telling me, then what is this object? This is kind of a flux across the horizon, and therefore I can call it delta Q symbolically. Remember, for the unperturbed horizon, there is no killing isometry. So I'm defining this flux with respect to the background killing vector. It is only possible because I'm doing it in first order perturbation. Okay. So therefore, from this, I will be able to write kappa by 2 pi delta S equal to, what should I say, delta Q. Use the same notation because this is also integrated flux between bifurcation surface, total integrated flux, whatever has fallen in between bifurcation surface and the future horizon. And if I use Hawking temperature, I will be able to write down T delta S, which is akin to the what we call the cautious relationship in the thermodynamics, that heat flow, there is no PDV omega dH terms here. Okay, this is like heat flow going into the horizon, which will giving me the TDS term. Clear? Okay. For GR, this is a beautiful derivation. Okay. First thing to notice is that things look ugly if this is non-zero. Right? If it is non-zero, in the linear order, there is no first law. Okay. As it turns out, remarkably, okay, that if you use, now in fact, there is a general proof, thanks to Shubhayo's group and many other people, it turns out that order by order you can show for any theory of gravity, there is a remarkable symmetry on the horizon, background killing horizon, for which this term exactly vanishes when you choose rho as the black hole entropy, integrated. This term, order by order, for every theory for which you have HAB as the equation of motion, rho as the black hole entropy obtained from Wald entropy, this term vanishes. The first order part of this term vanishes. Okay, this is remarkable. There is no reason for that to happen. Okay, but it turns out things are conspired such well. Let me give you an example. Suppose I take F of R theory. Okay, that's easy to check. Let me do it here. See how remarkably this guy is cancelling. Okay. Let's take F of R theory. F of R theory or L of R theory according to our notation. L of R theory. In L of R theory, what was rho? Remember? Tell me. 1 by 16 pi g F prime R. Okay. Because L of R I have written as 1 by 16 pi g 1 plus F of R. Remember that was the notation. Okay. I'm not putting any alpha. You can always put alpha inside. Okay. Okay. Let's see what will happen. So what is the equation of motion of this theory? Okay. Vary this Lagrangian. I leave it for you to do this. You will see HAB KA KB is given by F prime R, okay, RAB KA KB minus KA KB del A del B F prime R. Let's check this. This is the equation of motion of F of R gravity. Okay. HAB will be this. Okay. Of course, there is a RAB KA KB for GR, which is always there. Okay. I'm only writing the HAB KA KB part. Okay. Let's go ahead with this. With this, let's calculate what is this object. So therefore, rho 1 by 16 pi g, calculate rho R alpha beta K alpha K beta minus H alpha beta beta K alpha K beta minus D2 rho D lambda 2. And what is this object? F1 by 16 pi g F prime R alpha beta K alpha K beta, that is rho, and H alpha beta is minus F prime R alpha beta K alpha K beta, and this minus is plus K alpha K beta del alpha del beta F prime R. And this object I've shown you for affine parametrization. In fact, you can try it non-affine also, everything will work out. And took, and we'll have 0. It's remarkable, even if you have rho is not 0 for F of R gravity, this entire thing actually vanishes completely. See, you don't need to vanish this guy completely. You just have to show the first order part is 0. Okay, there is no first order part because we are doing linearized variation. But in F of R gravity, remarkably, it exactly goes to 0. This is first noticed by, I think, Jacobson, Kang, and Myers on their paper on black hole entropy. They first noticed it. And then, even for F of R gravity, this is true. Valid for, hey, we have done one, this what is called? One tutorial. We don't have to do that. Valid for F of R or L of R. Even if when the entropy is not proportional to area, it is proportional to some F prime R, still there's a remarkable cancellation goes in, and you can show. In fact, you can try. If it is Einstein-Cosmology gravity, things will be not that easy. Okay, or full log gravity, it will be more complicated, but you can show by a good calculation that just like F of R theory, in fact, what will happen for log gravity is that only the first order part will cancel out. Okay, but again, even with that entropy, this is true. I again emphasize, please understand the non-triviality of this. Entropy, I am changing entropy to 1 plus rho. Equations or motions are adjusted exactly such a way, the relationship between the Wald formula, that always this equation turns out to be correct. Okay. So details. So this is area, then this is almost clear why it should happen. it is not area, then also things conspired in such a beautiful way. So what it shows, just like Wald also showed, that any diffeomorphism theory of gravity, okay, as long as there is a black hole solution and as long as some good properties like stability, okay, cosmic censorship, all those things are hold true. In that case, it seems the thermodynamics of black hole is a generic phenomenon. It is independent of the equation of motion. Okay. Just like it was first discovered in Einstein gravity by seminal paper by Hawking, Bardeen, Carter, and then by Bekenstein, the second law. But now it is clear that all these things, Einstein theory, it is easier to prove, but this is a characteristic property of any black holes, any diffeomorphism. In fact, why not? Maybe some extra fields also things will go through. Okay. In fact, now people have shown that the first law, second law, everything is valid, provided any theory of gravity which is perturbatively expandable and general relativity. Shubhai has worked on this, I think, the related question related to the second law. And then other people like Harvey Rial has given this proof, how to do it for a general theory. Okay. Because me, Aaron, and my collaborator, we have only worked it for theory with was theory, Lovelock theory, but now recently, even 6 months ago, a year ago, okay, Harvey Rial has given a full general proof that how to do at least linearized second law. I think second law for any theory which is close to Einstein relativity in order by order. Here there is no such assumption. Here everything is exact in alpha. The expansion is only in the thetas and sigmas. In their case, it's a little bit different. Okay. So this is where I would like to stop the result. What we have seen in these 5 lectures is only a glimpse how the things to be calculated. We have seen there's a remarkable Wald formalism, which is sufficiently general, motivated from the covariant phase space formalism in classical mechanics, in classical field theory. And that formalism gave us a very powerful and very, very elegant way of define what we call the stationary version of the first law. And that version is, those strange is very powerful. Any theory of gravity, as long as there's a diffeomorphism invariant, because I have to take the Lee file, I will be able to calculate the black hole entropy as the Noether charge of the time isometry. At the end of the analysis, it is clear that black hole entropy is the Noether charge of the time isometry. There is a different way of doing it. Again, started with Wald and then Jacobson and other people, that there is a physical process first law where I can do things by integrating across the horizon. One advantage of this is that I don't have to go to the infinity. I don't have to talk about asymptotic quantities. Sometimes asymptotic quantities definition is difficult. Okay. Okay. If the asymptotic conditions are not simple asymptotic flat, it is not easy. But this, nowhere I have used properties of the asymptotic conditions. Okay. But I have to use certain kind of stability property of black hole. If you get something, you have to give something. Okay. There is no free lunch. Okay. So only indicative things is that, so I should tell you the question of second law for an arbitrary theory of gravity at arbitrary order of expansion, okay, is still a open question. So for example, there is no exact second law till proven for Gauss-Bonnet gravity. In fact, there are possible indications the second law may not hold true, but then people have suggested possible buyout also. Okay. Anyway, that issue is still open. We don't know. Similarly, if we do not do this alpha expansion, perturbative expansion around general relativity, is not clear how will you prove first law, even let's say how will you prove zeroth law. Those are the open problems. Okay. There's a remarkable relationship between laws of black hole mechanics and the holography. Okay. And a lot of people have worked on it. That is also extremely important field, and a lot of open questions are there. Therefore, go ahead and solve them. Thank you.
Let us thank Professor Sudipta Sarkar for these wonderful lectures. And we are really grateful that since Shumanta could not take the class, he stepped in on a very short notice. Actually, he prepared all these lectures and he stepped in.
Now, I should add that I should thank Shumanta. I have mentioned in the beginning that he has really helped in preparing. preparing this lecture notes. So part of thanks should go to him.
Yeah. Okay, so let us thank the speaker again. Thank you.